Okay.
Dark matter and dark energy.
Sorry.
In the beginning, just when it was created, two of the most important forces in the universe came into existence: dark matter and dark energy. In the early 1900s, scientists had the technology to observe galaxies. And then when they observed the galaxies, we realized that the acceleration at the end of other galaxies were constant with the end of the middle. So think of it like this. Einstein and Newton both says that the more mass an object has, the more gravity that they have. Therefore, we can estimate the mass of an object by its gravitational pull. Things closer to the sun, for example, are more affected by its gravitational pull than things further away. What we find out is that the acceleration at the outer sides of the galaxies did not correspond to the inner parts. So imagine there's a big city, okay? And the city has traffic, but no matter how much traffic there is, the speed of the cars remain constant. Yet, there aren't any car crashes or anything. So, why would this happen? How does this work? Why does the speed remain constant? So that means there must be something out there, some kind of property, some force, which is holding these galaxies together, so that the gravities remain constant, yet they are still able to exist. But what is this force? This force is called dark matter. And so far, all that we really know about it is that it's dark. The thing is that we have not been able to find the actual dark matter particles, but we do know that they exist, because they don't absorb or give out light, but they bend it, much like how your glasses bend light. Since the discovery of dark matter, physicists have looked at all the objects in the universe much differently. For example, black holes are thought to be dark matter because they don't give out light and they also bend light. So we call these gigantic clusters of darkness machos, or massive compact halo objects. But the thing is, there aren't enough black holes in the universe to make up for all the matter. If there were, we would be dead by now. Other good candidates for the dark matter particle are axions and neutrinos. And although there are a lot of axions and a lot of neutrinos in our universe, they are both way too light. That's why scientists think that there must be some other particle, some exotic particle that we haven't discovered yet, that is dark matter. So we call these particles WIMPs, or weakly interacting massive particles. And the reason that they're weakly interacting is because they don't collide with protons, neutrons, and electrons, ever. A team at Fermi has been trying to find these particles for the last 2 years. They have made these hockey puck-like plates made out of germanium and have frozen the germanium particles at sub-zero temperatures. Not only is there a 1 in a million chance that a particle would actually hit one of these germanium sub-zero temperature particles, but there are plenty of other particles that constantly distract these germanium plates. For example, the neutrinos. you know that
Sorry. So basically, dark matter has some of these properties, which is they can deflect light rays, which means that we can't see them, but we can see how light bends around them. So we have these things called gravitational lensing, which can sense these dark matter objects, but we have not found the dark matter particle as of yet. Our universe consists of 23% dark matter, 4% light matter, so like us, the Earth, etc. And the other 73% is called dark energy, which I will continue in this video.
Now you know that 23% of the universe is dark matter, and the 4% is what we can observe, so light, electrons, protons, that stuff. But what is the other 73%? Well, that is precisely what scientists have been trying to figure out. This 73% is what we call dark energy. See, here's what happened. When Einstein was coming up with his famous equation E equals mc squared, he realized it could not be possible, because that would mean that the universe had to either expand or retract. So he came up with a repulsive vacuum energy, or a constant energy called the cosmological constant. But that is what we refer to as dark energy today. But back then, Hubble said that the universe is accelerating. So Einstein threw away his theory and called it his biggest blunder. But of course, now we know that his biggest blunder is our greatest discovery. We later found out by using type 1a supernovas that the universe was in fact accelerating at a quicker rate. And this was a huge discovery because we thought it was actually slowing down. That means that galaxies are actually moving away from each other. It's kind of like a room, a classroom with a bunch of desks and chairs, okay? Imagine that the room was getting bigger and bigger, and so the chairs were actually moving away from each other, but the chairs themselves do not become any bigger or smaller. Just like how our galaxies do not expand, but they repel from each other. Our galaxies do not expand because of dark matter, but they repel from each other because of dark energy, which is the force of repulsion, which means that E equals mc squared is correct, which means that Einstein got the last laugh, although he is dead.
I apply my battle theory. Minds are relatively blown, so take a seat, Steve. Oh, I see you brought your own. I'll school you anywhere, MIT to Oxford. All your fans will be like, that was awkward. I'm as dope as two rappers, you better be scared, cause that means alpha E equals mc squared. You got no idea what you're messing with here, boy. I got 12-inch rims on my chair, that's how I roll. You look like someone glued a mustache on a troll doll. I'll be stretching out the rhyme like gravity stretches time. When you try to put your little pea brain against this kind of mind. On the west, on the Snoop Dogg side, I'll be dropping that apples on your head from the shoulders of giants. Giant whose shoulders you'd have stood on if you can stand. I'll give you a brief history of pain with the back of my hand. You can't destroy matter or me. For serious, ripping holes in you bigger than the hole in your black hole theory was. There are 10 million particles in the universe that we can observe. Your mama took the ugly ones and put them into one nerve. You wanna bring the heat with the mushroom clouds you're making. I'm about to take raps from straps like Carl Sagan. And while it's true that my work is based on you, I'm a supercomputer like a TI-82.
What that was
Dark matter and dark energy.
work, technology. Okay, so this thing this thing is like a graph, all right? 5 billion years ago, the amount of dark matter and the amount of dark energy started to exchange. So dark matter became less, and dark energy started increasing. And when dark energy increases, that means that repulsion also increases. So that means that the universe is actually, as I said, expanding. And the reason this is important is because scientists or theorists say that if the universe keeps expanding this way, all intelligent life forms will be frozen. So we'll all basically die, which isn't that great. And then, unless the dark matter and the dark energy change forces, or the properties change, or the amount of dark matter increases to a point where it can reach the amount of dark energy, the universe will keep expanding. But scientists have used this theory, like dark matter and dark energy, to combine it with the gigantic theory that they want to make of how the universe works, right? And theorists say that when they find out this gigantic theory, when they make it, they can ask some of the deeper questions, like why would the universe create dark matter and dark energy if it was to be its ultimate demise? Yeah. Thanks for listening.